So yeah, I'd like to firstly thank organizers for having me in this meeting. And I'd also like to thank all the participants, especially it seems to be a tricky time even for people in Australia. Today I'm going to talk about our process enrichment in Gaia-Enceladus using a GALAH DR3. So my name is Tadafumi Matsuno. I'm from Kaptein Astronomical Institute at the University of Groningen in the Netherlands. So today, this is a periodic table, and today I'm going to talk about these heavy elements. These heavy elements are not synthesized through explosive nucleosynthesis at the end of the life of massive stars. And instead, these heavy elements are produced by neutron capture reactions. So in this figure, nuclei are plotted in a figure showing atomic number and atomic weight. And as you know, there's a valley of stability. So if neutron capture reactions occur slowly, the reaction should proceed along this valley. But in some environment, the neutron flux can be so high that the time scale of neutron captures becomes much shorter than the time scale of the beta decay. And in this case, the reaction should proceed near the neutron drip line. If this reaction occurs, firstly, neutron-rich nuclei are produced, and then these unstable neutron-rich nuclei experience a number of beta decays until they hit the stable nuclei. So the first process is called S process, and the other called R process. Here's a close-up of this region in this figure. Although the horizontal axis is changed from atomic weight to the neutron number. So it's a bit different, but basically the same information. So in S process, if there is an unstable nuclei, this nuclei cannot capture additional nuclei before it experiences beta decay. So in S process, we cannot produce this nuclei because of this unstable nuclei. But in R process, more neutron-rich nuclei can be produced. So after beta decay, this nuclei can be synthesized, and this isotope can only be reached through R process. Some elements have isotopes that can only be reached through R process, and these elements are called R process. The site of R process nucleosynthesis is still debated. The most promising site is neutron star mergers. This is supported by the observation of the afterglow of gravitational wave event GW17 or H17. It is also supported by the numerical simulation of the nucleosynthesis, which successfully reproduced the observed R process abundance pattern of some R process enhanced stars in the Milky Way. But the question remains in the daytime distribution. It's not clear if the expected daytime distribution of neutron star merger can reproduce the observed R process abundance trend of stars in the Milky Way. Today, I'm going to study this by studying stars in this metallicity range around the -1 in FAYH. And below this metallicity, the expected number of R process nucleosynthesis events becomes small. So small in each galaxy. So the evolution of R process abundance becomes stochastic. At higher metallicity, stars are formed in Milky Way disk, where there might be or there would be abundance gradient, and also the stars move because of radial migration. What is good about stars in this metallicity range is that these stars would likely have been affected by multiple R process nucleosynthesis event. And also at this metallicity range, we see number of kinematic substructures among halo stars. Examples are Gaia-Enceladus, Sequoia, and HERMES streams. We also see some stars formed in the Milky Way called in-situ population. And these kinematic substructures are considered to be the signature of a past galaxy accretion. So by studying stars in different kinematic substructure, we can study chemical enrichment in different galaxies with different star formation history. Today, I focus on one particular substructure, Gaia-Enceladus. And I think many of you already know about the substructure, but let me briefly describe its basic properties. So it is basically the most significant kinematic substructure seen among nearby halo stars. The kinematic property is like this. So it's most dominant in the space of angular momentum and orbital energy. And it is considered to be the signature of the last major merger that Milky Way has experienced. The chemical property of Gaia-Enceladus is characterized with low magnesium or low alpha element abundances compared to high alpha element abundances in in-situ stars. And this is considered to be a result of different star formation timescale and delay time of type I supernovae. The progenitor mass is estimated to be around 10 to the 9th, and the epoch of the accretion is estimated to be around 10 giga-years ago. So why do we study R process enrichment in Gaia-Enceladus? There are several advantages. And one is that Gaia-Enceladus stars are formed outside the Milky Way, so they are formed in a different environment compared to stars formed in situ. Yet these stars can be found in the solar neighborhood, so many of Gaia-Enceladus stars are accessible to high-resolution spectroscopy with 4-meter class telescope. The second point is that the previous studies have characterized light element abundances of Gaia-Enceladus, especially magnesium over iron. So we can now really focus on heavy element abundances. And this abundance feature of Gaia-Enceladus has been well understood, and it is understood as a result of different star formation efficiency in the sense that Gaia-Enceladus has a lower star formation efficiency. So that's more affected by the nucleosynthesis process with delay time. So this enabled us to study R process enrichment in different environments by comparing Gaia-Enceladus stars and the in-situ stars. So in this work, we use European abundance from GALAH DR3, and this is the solar spectrum. This image, I actually took this image from the website of GALAH. And the European abundance is derived from this line. So the GALAH team has provided an excellent data set of European abundance like this, showing European over iron as a function of metallicity. But since we want to study the European abundance of low metallicity stars, we have to be a bit careful about the detection limit, which is noted here. So the first thing we did is to check the detection limit as a function of stellar parameters, signal to noise ratio, and the metallicity. So here, I divided the stars according to their signal to noise ratio. This is the lowest signal to noise ratio, and this is the highest signal to noise ratio. And in each bin, the number of stars are indicated by the size of the circle. And the color shows a fraction of stars with European detection. So basically, blue color means most of the stars in this bin have a European measurement in GALAH DR3. And as expected, the detection rate decreases towards lower signal to noise ratio and higher surface gravity and lower metallicity. So we decided to focus on this range because we don't want our distribution of European abundance to be affected by this detection limit. And we actually checked the spectra of stars in this bin, which is close to the edge of the selection box. And as you see here, the detection of European line seems to be quite robust. So we are quite confident that the reported European abundance are reliable. At least we focus on this range. we now kinematically select Gaia-Enceladus stars and in-situ stars using a radial action and angular momentum. So actually, the selection of Gaia-Enceladus, we just follow the previous one. And I think Diane is going to talk about this kind of selection in the talk right after me. And we also selected in-situ stars using a radial action. And we verified this selection using stars with metallicity around -1, where chemical separation between Gaia-Enceladus stars and in-situ stars are quite clear. So this panel, we plot the magnesium over iron abundance of stars in this metallicity range from GALAH DR3 and as a function of radial action. And below this upper boundary for the selection of in-situ stars, most of the stars have high magnesium over iron abundance ratio, while above this lower boundary for the selection of Gaia-Enceladus stars, most of the stars have low magnesium over iron abundance ratio. This can be also seen in this panel. So we just wanted to confirm that we have the same picture in magnesium over iron abundance as previous studies. So this is the data from GALAH. And we see a clear difference in magnesium over iron abundance difference between Gaia-Enceladus and in-situ stars, in the sense that Gaia-Enceladus stars are lower in this abundance ratio compared to in-situ stars. And this population seems to merge at the metallicity of -1.5. So this is good. We confirm the previous findings with GALAH dataset. We now move on to europium. So this is what we have with GALAH dataset about the europium over iron. And here plotting a europium over iron as a function of metallicity. So it seems to be clear that the Gaia-Enceladus stars has a higher europium over iron compared to in-situ stars. We also plot this abundance ratio relative to magnesium abundance. So plotting europium over magnesium as a function of metallicity. Actually, this is a better indicator when we discuss R process contribution in the system, because compared to iron, magnesium has a simpler nucleosynthesis origin. Like, while iron can be produced by either quark supernovae or type I supernovae, magnesium is mostly produced by quark supernovae. So we can study the contribution of R process nucleosynthesis relative to the chemical enrichment by quark supernovae. So again, okay, yeah. Again, the Gaia-Enceladus seems to. It is clear that Gaia-Enceladus stars have high europium over magnesium abundance ratio compared to in-situ stars at fixed metallicity. So yeah, this is a good thing, but I think we have to call this a kind of confirmation, because a number of previous studies have witnessed a hint of high europium abundance of low magnesium abundance of halo stars with low magnesium abundances. Yeah, for example, Shiaki et al. 2013 indicated that stars with low magnesium over iron ratio seems to have high europium over magnesium abundance ratio. What GALAH provides is a clear confirmation of this kind of trend with large, homogeneous, and well-characterized data set. And before interpreting the R process enhancement, we confirmed that this europium enhancement is not due to S process by investigating the abundance ratio between S process element and R process element. And the important thing here is that Gaia-Enceladus star does not show higher S process contribution compared to in-situ stars. So, which means the high europium abundance is not due to S process, which should be caused by R process. We now move on to the interpretation. The key is the delay time distribution. Neutron star mergers are expected to have some delay time because this event needed 2 neutron stars to merge, so it takes some time. And actually, the mechanism is kind of similar to that of type I supernovae. So the shape of the delay time distribution is expected to be roughly the same as that of type I supernovae. So this is the observational constraint on the delay time distribution of type 9 supernovae. And as you see, compared to the delay time of quark supernovae, which are very short, the delay time of type 9 supernovae are quite long. I mean, some type 9 supernovae can occur long after the onset of star formation. And this is a key. Here is a model, chemical evolution model for a dwarf galaxy, showing europium over magnesium abundance ratio as a function of metallicity. Since we assume that all the europium come from neutron star mergers, there is no source of europium in the early universe. But as time passes, neutron star mergers start to occur, so that's why this ratio keeps increasing. If the system is higher star formation efficiency, the entire evolution will be shifted to the right, because while this ratio is mainly dependent on the time, while metallicity is also dependent on the time and the star formation efficiency. Basically, system with higher star formation efficiency has higher metallicity at a fixed time. So that's why the entire evolution will be shifted to the right. So if we compare the europium over magnesium abundance ratio of these two systems, the system with lower star formation efficiency would have higher europium over magnesium at a fixed metallicity. And actually, there's nothing special about this explanation. Similar mechanism has been suggested to explain stars with low magnesium over iron abundances by assuming low star formation efficiency and the delay time of type 1 supernovae. And if you don't have a delay time in our process enrichment, the evolution would look like this. So the abundances would not depend on the star formation efficiency. So here is a comparison with observation and the model. The qualitative agreement is not very good. That would be probably due to the simplification in the model calculation, and also the uncertainty in the yield of nucleosynthesis. But the quantitative agreement is very good. Like we can reproduce the high magnesium over iron abundance of in-situ stars and low europium over magnesium abundance of in-situ stars. So which indicates that high europium over magnesium and low magnesium over iron of Enceladus seems to be a result of lower star formation efficiency and the delay time of neutron star mergers and the delay time of type 1 supernovae. We now add 3 galaxies in this plot: Fornax, Sagittarius, and LMC. These 3 galaxies are quite massive and still surviving around the Milky Way. And these 3 galaxies are known to have a low magnesium over iron abundance and high europium over magnesium. And these 3 galaxies have extended star formation history compared to Gaia-Enceladus or in-situ stars. So we now put these 5 systems into one figure here: europium over magnesium and magnesium over iron. And this is again the chemical evolution track. If a system had stopped the star formation at early times because of the short star formation timescale, then the system would have a low europium over magnesium and high magnesium over iron. If a system has prolonged star formation, then the europium over magnesium would be high and their magnesium over iron would be low. In-situ stars and Gaia-Enceladus stars are located here, and other satellite galaxies are located around here. So they can be placed on the same plane as the relation between in-situ stars and Gaia-Enceladus. And it seems like similar mechanism seems to be operating in these 3 massive surviving dwarf galaxies. So yeah, this is basically it. And here is a summary. And I'm happy to take any questions. Thank you.
Thanks a lot. Is there any questions? Let me see. Post your questions either in the chat or raise your hand, please. I don't see any raised hands. Or in case I don't see your hand raised, please unmute yourself and ask questions. In the meantime, I might ask a question. So with the connection with the star formation efficiency and the European abundance, and you put the satellites also on this plot. Is there any way that you can pin down the star formation efficiency of those galaxies with this kind of measurements?
I have to say it would be very difficult because the exact location would depend on the duration of star formation, and also yeah, actually I think that in order to constrain star formation efficiency, we first need to constrain the delay time distribution of neutron star mergers, because you know, we can't sort of do things at the same time using this one, you know, constraint. So yeah, so at this stage, I would say it would be very difficult, but maybe once we constrain the delay time distribution of neutron star mergers from independent observation, maybe like from observation of more neutron star mergers with gravitational wave detectors, or maybe with observation of gamma ray burst, maybe we can constrain the star formation efficiency using this abundance ratio.
Okay. Any other questions? There's a question on the chat by Vasily Belokurov. Do you want to unmute yourself and ask, or should I read it out?
I don't mind really.
Oh.
Either way. Hi, Tadafumi.
Hi, Vasily.
So why do you let me also switch on the video. So why do you favor the neutron star mergers versus core collapse if the europium versus iron is high and flat, just like your model for very short time? So I didn't understand. You said, look at this. That would be a prediction of an alternative model, right? So when you don't have a distribution of time delay, and then when you show us the europium track, it looks like that, right? It's high and flat, isn't it? I mean, it's you can continue it to the pretty low metallicity to -2-ish, right, with other measurements. And so then I didn't understand the interpretation.
Okay. So I think the key is the lack of difference when we assume quark-Collar supernovae as the origin of a neutron, as the origin of R-process element, because in the case of R-process nuclear synthesis by quark-Collar supernovae, the R-process abundance would not depend on the star formation efficiency, because basically europium and magnesium are produced at the same time. So it is actually true that both of the systems seems to have a flat trend in europium or magnesium as a function of metallicity. But I think, yeah, I mean, yeah.
It is a bit of a mystery, but it's not like on the face value, very superficially, it looks like it's going against this neutron star merger interpretation, very, you know, in the simple terms. Maybe there's something hidden that I don't understand, but it's like, looks pretty flat, no?
Yeah, I mean, sorry,
I guess no, I guess there is no easy answer to this kind of thing, and I propose to move that to the Slack channel for further discussion, so we can move on to Diane's talk.
Sure. Yeah. Thanks, Tadafumi. Cheers.
Thank you.